So it's the last chapter.
Whoa! Wait, what are we doing after this?
After the last chapter,
Yes.
we'll take a test on chapters 25 and 26 and review for the AP exam by primarily doing old AP exams
I could do a book card after
Okay.
the last chapter.
after the last chapter.
Bit.
So remember earlier we did regression lines.
I
Right?
missed those.
You missed those?
Bring them back.
Well, there's some parts of them that we will bring back for this. Okay? We call that bivariate data. The X changed and the Y changed.
Oh.
Okay? And we looked at summary statistics and residual plots and all that kind of stuff. Do you remember looking at residual plots?
When you
Yes.
did it sideways and it was like,
These are
it
good.
had to be evenly distributed around the line.
Yes. Yes, you don't want. Yes, all that stuff comes up in this unit.
Well, see, we learned things in this class.
Excellent. So here's a reminder using a homework problem from chapter 8. So we've got this Oakland passengers. The scatter plot below shows the number of passengers departing from Oakland, California airport month by month since the start of 1997. Time is shown in years since 1990 with fractional years.
Oh, God. You were there for that.
I was alive for that. I wasn't in Oakland in 1990, but to represent each month. Okay? So here's our plot. This is just our scatter plot. Okay, notice it gives us some information. On these, most of the time, you're going to be given a computer printout of information, very similar to this. Okay? So, interpret the slope. What is the slope?
The slope is the
So,
average.
The slope is given. What
I was
is the slope?
interpreting it.
I'm not interpreting yet. I asked, what is the slope?
I don't know. 59,704.
It is indeed.
Woo! Oh, look. That's good. 0.4, because there's fractional years, obviously.
Right. So, what does that represent? What were you going to say?
The average change in passengers over years since 1990. Or the change in passengers over years since 1990 on average. Or something like that.
Okay. Here's something that the AP would like to see something a little bit more like this. Although that's not wrong,
It's not right.
it's not as right as it needs to be. Okay. So, the number of passengers departing Oakland Airport so
That's the immaculate heart we do, actually.
So you have to make sure that you give the context. Increased approximately, and the reason we have to have approximately is because it didn't do this every month. Or you could say on average. I would take that also.
That's what I said.
Yeah. 59,704.4 passengers per what?
Year since 1990.
Well, just per year. In the years since 1990. Okay, what about the intercept? What would that tell you in this particular one?
In 1990, how many passengers?
Yeah. So the model approximates that in 1990, what was it? 28,000? No, 282,000.
That's so many.
584 passengers.
If you said people there, would you get points off? That's like a legitimate
Probably.
question.
Um, I tried to keep it to whatever they said in the problem.
Okay.
You-
So maybe. So
I guess it's possible. I don't see it happening, but
what if you called in like how's a palm noise?
If turtles, I feel like is
Turtles can be passengers too.
but you're actually right. Would you count off for turtles?
Yes.
departed Oakland Airport. So one of the things that we did also was talk about R squared. Do you remember what that told you?
Like the straightness of a lot of residuals or something.
I'm sorry?
The straightness of the residuals.
No?
No.
How far the average?
The
drop
square.
was.
Yeah, if it was a square.
Yeah, it's squared, so there's just
How,
No,
if it was a line.
No, if there's a
How
line,
is it? How good did the model fit?
sort of.
but it's the average distance from the dot to the line.
That
But
was-
it
I
makes
would like
it
it to be
square.
noted that was
So-
the first thing I said.
No,
Here
but
we
it
go.
makes it makes the square, and the square is important, dude.
71.7% of the variation
In distance from the line.
in the number of passengers departing Oakland Airport. A lot more people departed Oakland.
That'd be points off.
Is accounted for
By the model,
by close
the equation.
by the number of years since 1990 in this model.
Wait, I don't get
This
this.
is why I get these wrong. 'Cause it's just so many details.
It just sounds like a
Listen
lot
to
of words,
details.
but like a lot of nonsense.
But apparently,
Well-
all the nonsense is important.
So
It's very important.
the variation in the number of passengers is accounted for by what other variable?
The years, the variation of the years.
So you could say by the variation in the number of years, by the number of years.
So basically,
In this
it's
model.
like neither one of them are totally correct. They're both varying a little bit.
Well, they both vary. So how good a model is that then?
That's
Agreed.
kind of okay.
It's pretty good. Not perfect.
We can rock with it.
There are other things that apparently,
Should we look at the residuals before we resume?
well, it didn't ask us about that, but we will be looking at residuals.
Okay.
Just be patient with us.
I see. I
No
think I see it.
grasshopper.
Am I grasshopper?
All right.
Okay.
So here they talk about S sub B, and you're like, S sub B, there's no S sub B there. Well, the computer doesn't always write it.
Stupid computer.
So the standard deviation in the number of passengers for the model is 104,330.
What is S?
It's in the error.
Standard error.
So how much did, it's not quite the standard error. but it's the standard deviation of the residuals.
So it's not different from S?
It's the same thing.
Okay.
Yeah, they give you, the printout usually says S, and sometimes the question says S sub E. It's the same thing.
Yeah, please go to the restroom.
You may.
Bye, Lily.
All right, so here's the whole question. In this one, we had every data point from, what was it, 1997 to 2007.
That's a lot of years.
Right, and they did it, by the month. So we have every data point we could possibly want. But what if we only took a sample of these?
It would look a lot more like a line.
Middle school softball girls are dismissed, please. Teachers, if you would dismiss our middle school softball. Thank you.
So what if we took a sample and we wanted to make a regression equation from the sample? We would have less confidence in it, but frequently we can't get all the data points. Right? We're going to just take a sample, which is what we've been doing all along with I'm trying to think of the word now.
Our inferences?
Thank you, our inferences. There's too many words in statistics.
Yeah. And they're all hard to say. Statistically significant?
It's a tongue twister.
So we could still make a regression line, but the question is, how good would it be?
It wouldn't be as good.
It wouldn't. Okay? It absolutely would not. But can we make it to where it's good enough? And the reason why you would want to make it good enough, I know that's set to your mouth. That's I'm not happy about this, is when you're trying to find, like if you're surveying something, it costs money to do a survey. And the bigger your sample is, the more money it costs. And if we can get a good enough one without having to do the entire population, that would be nice.
Because you just want to, project.
That's what an inference is. An inference is we take a sample from the population and we go, from this population, we're going to infer, we're going to go, well, if we meet all the right qualifications, that this is true or this is not true, or the mean is between this number and this number. Okay? That's a lot of what statistics is. It's inferential statistics. You're taking a population and taking a sample from that population, doing some work with it and going, okay, I think that based on this sample, this is what we know. All right. So the conditions are as follows. Okay, and these conditions, pardon?
You have to check those.
Yeah. The conditions kind of bug me on this one. I'll be just completely honest.
They bug me too.
The true relationship between x and y must be linear. Well, in just a second when we do a hypothesis test, our hypothesis is,
It's linear.
yeah, well, our null is that the slope is 0, which means there is no relationship. And then our alternative is going to be there's a linear relationship. And I'm like, I've already looked at the scatter plot. There's a linear association. I'm convinced of it. Sort of like you were convinced yesterday with the immediately.
No!
So now we're going to have statistical backing for that.
I feel like whoever these statisticians are that came up with this, they were just kind of throwing stuff at the wall, and some of it stuck, and they were like, we're gonna keep statistic kids in school.
So this is the part you were talking about the residuals. The standard deviation for y does not vary with x. So that means, where the plot thickens, where your residuals spread out one way or another, or there was some pattern to the residuals,
Yeah.
that's what that goes against here.
So it's saying that there can't be a pattern in the residuals.
Correct.
Okay.
So the standard deviation for y does not vary with x. Remember we said that the graph of the residuals should be the most boring graph ever.
Like
Because if
no
it
random
does have a
reason to it.
pattern, then
Then it's a little
not
more
linear.
exciting.
Right, if it has a pattern, then yeah, it's not a linear function.
So 1 and 2 are kind of the same thing.
Well, on 1, we're going to look at the scatter plot. So to see if we just look at this scatter plot, we go, yes, there's a linear association there. And then we'll look at the residuals to see
Double check if it looks linear.
exactly. Okay. And then the data points should be independent, which means the sample should be randomly selected from a randomized experiment or representative of the population. And when sampling without replacement, as always, less than 10%. What?
And she goes,
And for a particular value of x, the responses, the y values, should be normally distributed. So if you had just one x value but multiple y values, which can happen on this,
I guess if the dots
like
are
in
stacked,
April and May, same number.
no, it doesn't
In
work
April,
real well
they're
on this
different.
one because we're looking at time. But if we were looking at some other explanatory variable, let's say that people worked out this many hours and they lost this much weight, so there were different weights that they lost for that much.
lost 10, lost 6, but for 6 hours.
Right. So those numbers need to be normally distributed. They need to cluster around something. They can't just be all over the place. So you look at the distribution. If the distribution is skewed, n has to be greater than 30.
Wait. Oh, N. Okay.
All right. If n is less than 30, the distribution must be free from outliers or strong skewness. You're like, we keep doing this over and over again.
So basically, it really, really, really has to look linear and it has to be a random sample.
Yeah.
Okay.
So once these conditions have been met, you're going to do the standardized test statistic. That's another hard one to say. Standardized test statistic. So, and then on to the next page, the confidence interval.
Oh, look at those beautiful graphs.
Look at all them chickens.
So we're going to need to be able to figure out the standard error of the statistic.
Yes.
Before I just give you a formula for that, let me show you why it works the way that it does. We can't always do that real well, but here we really can. So there are 3 factors that influence the standard error of the statistic.
The sample size.
We're going to get to that,
Oh.
okay? That's actually going to be our last one. But you're exactly right. So if we were to sample over and over from the 2 underlying populations that these samples come from and compute all the slopes, in other words, if we were to pick some randomly out of this and pick some randomly out of this, which group of slopes would vary less?
The left.
The left.
Yep. So I said the first, but left works.
Can we write that?
Yeah.
I feel it.
So why? Well, the way I would describe this is that there's a smaller standard deviation from the regression line. Your residuals would all be really small on the one on the left, and then on the right, there's some small, some big. So a bigger standard deviation. What about this next one? Which one is going to be better?
The one on the right.
The one on the right. Why? Because there is a greater spread in X. if all of our x values are close to each other, it's hard to get a good line out of that. We need some spread for that. And then the last one,
The one on the right.
one on the right.
Because the sample size is bigger.
Right. There's a larger sample. All right, so the standard error of a regression line is given by this formula. S sub b, b stands for the slope here of the regression line. So that's the slope of the regression. And that's just the b, not the S sub b.
So what is the S?
Standard error
Oh, yours.
for the slope, which is b. If I'd noticed that it was written down, I wouldn't have to written it, but is equal to s over s of x times the square root of n minus 1. Okay, notice the bigger the sample size is, remember the sample size is n, the smaller the standard error is going to be. S of x is the standard deviation for x. So the more spread out we are in terms of the x, the better. And S is our standard deviation from the regression line. So the closer it is to the regression line, the less standard error we're going to have.
What is the X in the S of X? Is that what you were just saying?
Yeah, that's the standard deviation for the x. So how spread are you in terms of the x? All right, your book uses slightly different ones than this, and I'll just tell you, you'll almost never have to calculate the standard error. Okay, it's almost always given. Yes.
What is that thing that looks like an E mean?
Sigma.
Oh, the summation? It's a
Yes.
sigma.
Oh
What does that mean though?
That means add them all together.
Like,
So you're going to have a whole bunch of this
oh,
should,
because like the X is like all your like points.
yeah, all these different points. How far are they from the mean?
So would you square them, then add them together, or add
You
them
subtract and then square,
and then add them?
and then add that to the next one where you subtract and then square, and add that to the next one where you subtract and you square. Okay? So let's go just a little bit further and we'll do the example on Monday. So when the appropriate conditions are met, the standard statistic for the slope of a regression line is t equals b minus beta, which follows a student's t model with n minus 2 degrees of freedom.
Why 2?
That's a great question, and I actually have an answer for it this
Oh,
time.
heck.
Yay!
It's because there's two different things that we're doing when we do a regression line. We're finding the intercept and we're finding the slope.
Okay.
So you take off those two. When you're only doing one thing, like we're doing for a mean, it's just the sample size minus 1. There are times when degrees of freedom totally makes sense, and there are times where I'm like, what the hey? All right. So beta, by the way, is the slope of the population regression line.
So B is just the slope.
Of the regression line for your sample.
Oh, so then beta is for everybody.
Right.
Okay.
So, and that makes sense. That's just the formula that's at the bottom of the first page. It's the statistic minus the parameter. The statistic is for your sample. Statistics are for samples. The population is for the parameter. So the statistic minus the parameter over the standard error of the statistic. All right. We will do an example. We got 15 minutes still.
We're just rolling through this.
It's just, let's finish it.
Let's knock it.
Oh.
Finish him.
Yeah, Mortal Kombat. Wait. Mortal Kombat?
Yeah.
You Johnny Cage or Scorpion?
Probably more Scorpion.
I like Sub-Zero.
So, data collected by the Gallup organization over 6 decades.
I hate them.
You're going to like this one.
What?
You're going to like this example.
No.
I know, I'm changing the subject. You're
No,
going to like
sorry,
this
no,
example.
I'm loving this example.
Okay. Asked respondents the following question. If your political party nominated a generally well-qualified person for President of the United States who happened to be a woman, would you vote for that person?
Who said no to that?
Sounds pretty bad.
Oh, you would be surprised.
It's like Bang.
Yeah.
You're really nah.
Yeah, there are people who, of both sexes, who are like, no, I don't think a woman should ever be president.
Facts.
I'm not going to say that because
So-
we're going to tell you something after we're done.
Okay. So they've been doing this over and over and over again for 6 decades.
They ask people every year.
Decade.
Every decade.
Every
Do you
year.
like Gallup polls?
Every year for over 60 years.
And they're still saying no?
Sexism didn't die.
What?
No, he's right. Right. I mean,
It didn't just die.
Oh, no, we know.
know.
so the question is it lessening? One would hope.
Yeah.
Yes.
Let's turn to the data and find out.
So this is legit. This is a legit study.
Yeah.
Alright,
This is real stuff. That's one of
Gallup poll.
a real life Gallup.
this is one of the things I like about this class is that the things you read in the book, these are real studies.
Yeah, they'll even like put the little
It's-
Sexism is actually happening.
So
The poll should have just said, "Are you sexist?"
yeah, but no one wants to answer yes to that.
That is
Who wants to
What?
answer? Who wants to answer? It's like, "Oh, I don't look
No,
sexist."
really.
I'm still gonna say no.
All right. So,
Wait, what's like the justification for that?
pardon?
Like, what's the rationale behind that?
I don't know.
They hate women.
Yeah, but you can't like outright say that. Like people had to
That's why they're asking you
why,
for
and then it has to be like.
I think there are some people for religious reasons believe that women should not
like, pastor
rule
reasons.
over a man, and there's the whole. I mean,
Okay, yeah, no, fair enough.
all right. So a summary of the data analysis is given below, where the percentage of respondents who said yes is the response variable. That is, think about it in terms of that's the Y. And the year is the explanatory variable, where 37 would correspond to the year 1937. Okay?
Love it.
So
It's in the 1930s.
it gives you all these different things. So assuming that all the conditions for inference have been met,
Yay!
don't have to jump through any of those hoops. Find the standard deviation of the residuals and explain its meaning in context. Where did they give us that?
4.378.
Oh, yeah.
So 4.378.
What are the units for that? Just like
Oh, no, sorry. No, that's the standard error in the intercept.
0.07339.
4.55.
Oh, what?
The standard error of the residuals is the same as the standard error from our line. So it's 4.550. The observed percentage of respondents who said yes to the question differed from the regression model with a standard deviation of 4.55. So that's generally how much did it vary. It's a measure of the variance. So the standard error of the slope, where do you find standard error of the slope?
4.378.
Of the slope,
0.07339.
yeah.
What is the R squared ADJ?
I'm sorry?
What is the R squared ADJ?
Adjusted.
Adjusted for what?
I have no idea. I ignore it.
Outliers? Adjusted for inflation?
Could be.
I don't know what it's adjusted for.
Adjusted for population difference?
It may be adjusted for some outliers that occurred in the original data. All right, so as
Does that mean it's
I can't read my own writing here. Hang on a second. As different samples of the same size would have differing slopes, the standard deviation would be about 0.07339 for a collection of these samples. So in other words, if you took a whole bunch of samples of the same size, this would be the standard deviation for that. Let's stop there. I know I said we were going to get through it, but I do want to hand back your tests.
Oh, I literally forgot about that.
I did too.